called the unsteady vortex lattice method. Some people call it the vortex panel. UVLM. There is the steady version of it, which is the VLM. The AVL program is just based on the steady version of it, the very famous AVL program. And we'll consider the two-dimensional version. So the VLM, the steady VLM, is just straightforward, and it really can be programmed in maybe an hour or so. The unsteady 2D is a bit more involved because there is wake. And the three-dimensional is quite a heavy code, the three-dimensional version. Of course, I was talking about the three-dimensional version of the vortex lattice. It's just very straightforward. The two-dimensional version of the unsteady vortex lattice is a bit involved, as you see today. The three-dimensional version of it is heavily involved. So another name is the 2D numerical. Of course, unsteady. Linear fault theory. Although we can handle thick FOS, that's fine. So, by this we mean we have, say, here is your port, and we have some camber line. And this camber line pitches, plunges, maybe moves with you, and maybe flexible too, in the sense that while moving and doing this maneuver, it may flex something like this. It may change its shape with time. So now our Y camber is a function of x and time, can change shape with time. And of course, as it evolves, there is wake coming. And the wake is deformable wake. Wow, okay, anyway, so wake. Okay? So this is our problem. I'm going to solve it numerically. Just reminding you that the steady thinner fault theory this was the picture. Y is a function of x and t, right? And we distributed some vortices, and to make it analytically tractable, we distributed the vortices on the x-axis, not on the shape itself. So this was gamma b as a function of x, and this was our main unknown. How we determined it? What was the main equation that resulted in gamma b? What's the main equation? What is the main equation that resulted in the circulation distribution? I have a problem like this, and when I want to get gamma b, what equation should I apply?
The integral equation?
The what?
The integral equation of circulation.
Yes, how to get the integral equation of circulation. What is a fundamental?
No penetration.
The no penetration, exactly. I have nothing but the boundary condition, right? So the V normal is equal to the V normal due to motion. Here the motion is very simple. It's just this guy is moving like this with u, and here is the angle of attack. So the V motion is simply u times alpha. But how can we feel the camber? Here is the only way to feel the camber, dy camber by dx. Because we're applying the no penetration on the camber line. So this is the normal, the V normal here is this guy, okay? So this was our steady thin air fault theory, which we did in detail. Then the unsteady version of it what's the picture? Here is the picture. Here is your camber. So here is y just x only, it's not function of time, right? Here we have y of x and t, and also for analytical tractability, we assume circulation like Tudor-Sum, von Karman series, Schwartz, everybody, gamma b as a function of x and t, but if it's an unsteady problem, we have to assume wake, we have to account for the wake, and again, for analytical tractability, we assume flat wake on the x-axis, gamma wake of x and t, right? Now what's our main equation here? What's the main equation? How you determine your unknowns? Okay, is it sufficient? Conservation of circulation is just a single equation. Summation all gamma is equal to 0. Okay. Again, this is another scalar equation. How many unknowns do I have here? How many unknowns do I have? How many unknowns do I have over there? How many unknowns? Come on, how many unknowns?
As many as
Yeah, I have gamma bound, but it's unknown at each point. It's a distribution. So I have infinite number of unknowns. So I need infinite number of equations. This is an infinite number of equations because this equation applies at every single point on the airfoil. Okay, coming here, how many equations do I have? How many unknowns first do I have? How many unknowns? Two, but this guy is infinite, and this guy is infinite also, right? Well, we have the conservation circulation of the quota relates the two, so let's focus on one. So for this one, I still have infinite number of unknowns, and I need infinite number of equations. How can I get these equations? What's the source of this equation? Come on, guys. What's the source of this equation? Of course, the no penetration. What would change? What would change? You always have the no penetration at your disposal. So V normal is V normal motion at every point. But like you said, that's okay, this solves the steady problem. We need something extra. This something extra can be the law of zero total circulation, can be quota, or both, whatever. Okay? Then what we're doing today is the numerical version of that. So we do numerical, we will relax small angle assumptions, we will relax the flat wake assumption, we will not place the singularities over the x-axis, we can place them exactly on the body surface. So here is the picture. Here is your thing. We're going to chop it, it's numerical. So we're going to discretize. The first thing to do numerically is to discretize your domain, right? And for each panel, we're going to place a vortex, gamma 1, gamma 2, yada yada, gamma n, okay? And then there is wake. So the wake, we will consider it as also a discrete number of vortices. Gamma wake 1, gamma wake 2, gamma wake 3, and so and so. But this picture is at a particular instant, right? It's at a particular instant. These gammas at this time, these gammas are in the wake from before. At this instant, if the airfoil is maneuvering, is changing its conditions, I have to shed vortices. So at each time instant, we have to introduce a new vortex at the trailing edge or near the trailing edge. Release it from the airfoil. So let's assume that it's at the trailing edge. This is gamma trailing edge, which is equivalent to gamma wake 1. Okay? The vortex dynamics dictate that if you have a vortex that is constant strength, doesn't grow with time, if it's a constant strength, then it moves with the flow. Okay? So each one of these wake vortices, they move with the flow, maintaining their strength. And how you determine their strength? Well, at the very beginning, t equals 0. What was the situation? Here is the situation. Shop your domain. So this is gamma 1 of 0, gamma 2 of 0, gamma n of 0. Okay? And we have here gamma trailing the edge of 0. All of these are unknowns. And there is no wake. Right? We just started our problem t equals 0. There is no wake. Okay? Don't spend your time just writing after me. You will have this, right? But just get the point. Okay, so gamma trailing edge. This is how many unknowns here? How many unknowns? How many unknowns here? N plus 1, right? So I need n plus 1 equations, of course, right? What's the n plus 1 equation? Let's see. Do you have any candidate? Let's focus on the n first. We have n bound vortices unknowns. Do you have candidate for any equations? The no penetration, of course. Okay? So the V normal 1 up to V normal n, this is equal to V normal 1 motion up to V normal n motion. Right? These guys are known. This is your motion, your input. So these n equations, and I need an extra equation because we have n plus 1 unknowns. So the extra equation in this one, you can have it as summation gamma is 0, right? Conservation of circulation. This can be replaced by Cotta condition. So that actually there are two versions of the UVLN. The one that we will study here is summation gamma equals 0. I like this one. You can replace the last equation by formulating your problem in the cylinder domain and asking that Q theta, right, or V theta, at theta equals 0, summation due to all things, this should be 0, right? This is Cotta condition. So you can replace the law of zero total circulation by this guy to get the extra equation that you need. Okay? Okay, so at each time step we have n plus 1 equations and n plus 1 unknowns. In the next time step, what happens? So t equals delta t. The circulation over the airfoil changed, right? So gamma 1 is now a new unknown. Gamma 2 is a new unknown at delta t. Gamma n is new unknown at delta t. And I am shedding a new vortex here. Gamma trailing edge at delta t. Again, n plus 1 unknowns at the new time step. But what happened to this guy? Well, from this picture, after we're solving for the unknowns, we have all gammas. So I can compute the velocity at any point, in particular this guy. I get the velocity at this point. How? This gamma over 2 pi r, this gamma over 2 pi r, this gamma over 2 pi r. Sum all these, you get the velocity here. So this vortex will move with the local velocity. Okay? So it will move a little bit from here down there a little bit. So this is gamma trailing edge of time 0, which is not unknown. It's already determined from the last time step. So at this time step, I have the same n+1 equations in n+1 unknowns. Okay. Let's do t equals 2 delta t. Gain gamma 1 of 2 delta t up to gamma n of 2 delta t, new unknowns, and I'm shedding a new vortex. Maybe the numerical code will tell me the strength of the new vortex is 0. When this happens, when the strength of the newly shed vortex becomes 0, when this can happen? No. When this can happen, the strength of the new shed vortex becomes 0. Steady, you reach steady, okay? So the code will automatically give you the strength. It may be 0, we don't care. Gamma trailing edge at 2 delta t, this is an unknown. Now I have how many point vortices in the wake? How many point vortices in the wake now? 2. This guy maybe moved a little bit like this. This is the one from before, so this is at delta t, and maybe the 2 delta t moves like this. Gamma trailing edge at 0. So if you want to connect the wake, it will look something like this. Okay? And you keep moving. So this is, in a nutshell, how we apply the program. We're going to do it in detail. We have today and next time, so we may even program it together here. Okay? It's very useful. You can do a lot with it. Any questions so far? Any question? Please, if you have a question, just stop me. Okay, so let's see that. So let's construct our system of equations. So like I said, these wake points, they are known. And here we have n+1 unknowns. So let's see how to construct one of these equations. We need to get the v due to gamma at one point and equate it to the v motion. So let's get this first. If you have a point here, P,